In the previous video, I have shown how radiative and minor Auger recombination works. The third mechanism that I will discuss is Shockley-Reed-Hall recombination. This mechanism is most important recombination mechanism in silicon-based solar cells, and we will therefore discuss it in more detail. In this video, I will first explain the underlying mechanism of Shockley-Reed-Hall recombination, and then some concepts are discussed concerning the carrier traps and trapping processes. Finally, the recombination rate will be presented, after which I will discuss each term of the equation in order to increase our understanding of the mechanism. The theory of this recombination mechanism was published in 1952 by William B. Shockley, William T. Reed and Robert N. Hall, which explains the name of this mechanism. It will be abbreviated with SRH in the future. SRH recombination is indirect recombination, and it is facilitated by an impurity atom or lattice defect. These defects introduce energy levels within the band gap which facilitate carrier recombination and are therefore often called recombination centers. Sometimes such energy levels are also called traps, as these levels can trap a free charge carrier. Once trapped, this charge carrier cannot move anymore and is said to be localized. For SRH recombination, we consider primarily deep-lying traps. Some traps have energy levels close to the band, but these levels do not contribute to SRH recombination and essentially only slow down the movement of free charge carriers. We will only consider the traps associated to SRH recombination. We distinguish two types of recombination levels. First, donor-type traps, which reside between the valence band edge and the intrinsic Fermi level. These traps are neutral when occupied by an electron and are positively charged when not occupied. Second, acceptor-type traps, which are positioned between the intrinsic Fermi level and the conduction band edge. These levels are neutral when they are not occupied by an electron and negatively charged when they are occupied by an electron. We call these traps donor and acceptor-like, since the charge state behaves the same as for donor and acceptor atoms. The following derivation of the recombination rate is performed for donor-like traps. However, the derivation is similar for acceptor-like traps except for the charge state. SRH recombination is based on four processes. Capture of an electron from the conduction band. Note that a donor-like trap can only trap an electron if it is empty, so when it already contains a hole. Subsequently, emission of a trapped electron to the conduction band. Then capture of a hole from the valence band and emission of a hole to the valence band. We will now discuss the rates of these four processes. The first process is given by the following expression. Since it involves the capture of an electron, it is proportional to the free electron concentration N. It is also proportional to the trap concentration Nt, since more traps can trap more electrons. As mentioned earlier, this donor-like trap can only capture an electron if it is not already occupied by an electron, which is incorporated by the trap occupancy of the electrons, F. This means that 1 minus F is the trap vacancy of electrons, so the probability that the trap is not occupied by an electron. Vth and sigma n are the thermal velocity and capture cross-section respectively, which we will discuss in a moment. Please note that the charge state of the trap is incorporated in the capture cross-section. Since this is a donor-like trap, the charge state is positive if the trap is unoccupied. The second rate has a simpler expression. It is again proportional to the trap density Nt and to the occupancy F by electrons, since this process involves trapped electrons. En is the emission coefficient of electrons, which is a measure of the emission probability. It also contains the charge state, which is neutral since this donor-like trap is occupied by an electron. The third process is similar to the first process, but now the capture carrier is a hole. The difference is that the hole concentration P is used instead of the electron concentration N, and the trap vacancy of holes instead of electrons, which is equal to F instead of 1 minus F. The capture cross-section is now related to holes and has a neutral charge state. The fourth process is again emission of a charge carrier, which means that it has a similar expression as the second process. Since it is a process in which a hole is emitted instead of an electron, the emission coefficient is now related to holes and has a positive charge state, as a hole can only be emitted from a donor-like trap if this trap is not occupied. Instead of the electron occupancy, the hole occupancy is now used, which equals to 1 minus F instead of F. The equations presented here are also valid for acceptor-like traps. The only difference is the charge state. This means that neutral charge states turn into negative charge states and positive charge states turn into neutral charge states. As mentioned before, I would go into more detail about the thermal velocity and the capture cross-section, and I will do that with an example. Imagine a trap state inside a material. The capture cross-section can be visualized as an area around the trap state, which we draw as a disk. The capture cross-section has the unit of area, so for instance square centimeter. Now imagine an electron approaching the trap state from the bottom left. If we now expand the circle to a cylinder with a length equal to the thermal velocity, we see that the thermal velocity and the capture cross-section together form the reach of the trap state in which it can capture an electron. The same explanation is valid for holes. We now have discussed all the process rates and we understand each of the terms in the equations. The next step is to examine the recombination rate in more detail. The recombination rate of SRH recombination is given by the following expression and follows from detailed balance of the rate equations that we saw earlier for the different capture and emission processes. Note that in this equation the charge states are omitted, as this is irrelevant for this explanation. The first combination of terms is related to the reach of the traps and the trap density. The recombination rate is linearly proportional to this expression, which is expected since a higher trap density or a larger reach will result in a higher recombination rate. The numerator expresses the probability of recombination, which is dependent on the free charge carrier concentration. In fact, this dependence is the same as for radiative recombination. The first two terms in the denominator indicate the occupancy of the traps. After all, when a trap is occupied, it cannot capture another charge carrier of the same type. Finally, the last two terms in the denominator are the emission coefficient, which indicate the rate of carrier emission. This is a rather complex equation and the mathematical derivation is omitted in this lecture. For more information, I refer you to the Solar Energy book. We can simplify this equation by combining most of the terms into a capture coefficient. All the red expressions are combined into a capture coefficient, leaving us with a much simpler expression. For N-type material, we are then left with three terms in the equation. the hole capture coefficient Cp, the trap density Nt, and the excess hole concentration. The same equation is true for p-type material, where p and n are interchanged, resulting in the electron capture coefficient and excess electron concentration. As I alluded at the beginning of this video, it is important to realize that not all trap states contribute to SRH recombination. Taking into account the occupancy of the traps expressed by the distribution function f, we can work out that the recombination rate per trap, the so-called recombination efficacy, and when we plot this recombination efficacy as a function of trap energy, we see a clear dependence on the energy of the trap state, and that the efficacy reaches its maximum if the energy of the trap is positioned between the quasi-Fermi levels of the semiconductor. This indicates that trap energies between the quasi-Fermi levels result in high recombination rates, while trap energies outside the quasi-Fermi levels show low or even zero recombination rates. Now to recapitulate, we have gained insight in three recombination processes: radiative, Meitner-Auger, and Shockley-Reed-Hall. We have discussed the mechanisms underlying these processes, and we have derived their recombination rates. With these equations, together with our knowledge about charge diffusion and drift, we can now take the next step, the ambipolar transport equation, which is presented in the upcoming video.